NENOMATICA, where mathematics meets YouTube excellence. Welcome to our mathematics video, where we'll be exploring the binomial square formula, a fundamental concept in algebra. Let's start by looking at the formula we'll be working with. For any real numbers a and b, the square of their sum can be expanded as a plus b squared equals a squared plus 2ab plus b squared. This formula is used extensively in algebra and is one of the key algebraic identities you'll encounter. Now, let's prove this formula step by step. First, we start with the binomial expression a plus b squared. Using the basic property of exponents, we know that the square of a term can be written as the product of the term with itself. So, a plus b squared equals a plus b times a plus b. Now, we'll use the distributive property to multiply these binomials. We multiply each term in the first parenthesis by each term in the second parenthesis. So, a times a gives us a squared, a times b gives us ab, b times a gives us ba, and b times b gives us b squared. Next, let's simplify each term using standard algebraic notation. This gives us a squared plus ab plus b, a plus b squared. Since multiplication is commutative, we know that ab equals ba. So we can rewrite the expression as a squared plus a, b plus ab plus b squared. Now we can combine like terms. We have ab appearing twice, so ab plus ab equals 2ab. This gives us our final result, a squared plus 2ab plus b squared. Now, let's see first example. We have x plus 1 squared. Using our formula, we can identify that a is x and b is 1. Now we can apply the formula. A squared is x squared, 2ab is 2 times x times 1, which is 2x, and b squared is 1 squared, which is 1. So, x plus 1 squared equals x squared plus 2x plus 1. Let's look at our second example, 2a plus b squared. Here, the first term is 2a, and the second term b is just b. Applying our formula, a squared is 2a squared, which is 4a squared, 2ab is 2 times 2a times b, which is 4ab, and b squared remains b squared. Therefore, 2a plus b squared equals 4a squared plus 4a plus b squared. For our third example, we have 2x plus 1/2 squared. In this case, a is 2x and b is 1/2. Now let's apply the formula. A squared is 2x squared, which is 4x squared. 2ab is 2 times 2x times 1/2, which simplifies to 2x, and b squared is 1/2 squared, which equals 1/4. So, 2x plus 1/2 squared equals 4x squared plus 2x plus 1/4. Let's summarize what we've learned about the perfect square formula. The formula states that a plus b squared equals a squared plus 2ab plus b squared. We've seen how to apply this formula to different expressions. X plus 1 squared equals x squared plus 2x plus 1. 2a plus b squared equals 4a squared plus 4a plus b squared. And 2x plus 1/2 squared equals 4x squared plus 2x plus 1/4. Remember, when using this formula, first identify what represents a and what represents b, then substitute these values into the formula and simplify. This formula is very useful in algebra and helps us expand binomial expressions efficiently. We want to expand the square of the binomial 2x plus 3. To solve this problem, we need to apply the square of a binomial formula. Let's apply this formula to our example. We need to identify the terms. In our expression, 2x plus 3 squared, we can identify that it equals 2x and b equals 3. Now, let's substitute these values into our formula. The square of the binomial 2x plus 3 equals the square of 2x, which is 4x squared plus 2 times 2x times 3, which is 12x plus the square of 3, which is 9. So our final answer is 4x squared plus 12x plus 9. Notice how we've expanded the square of the binomial into a trinomial expression. Now, let's look at our second example, which is more complex. We want to expand the square of the binomial 5x plus 2xy. We'll use the same square of a binomial formula for this problem as well. For this problem, we identify that it equals 5x and b equals 2xy. Now, let's substitute these values into our formula. The square of 5x plus 2x, y equals the square of 5x, which is 25x squared, plus 2 times 5x times 2xy, which simplifies to 20x squared y, plus the square of 2xy, which is 4x squared y squared. Therefore, the final expansion is 25x squared plus 20x squared y plus 4x squared y squared. Notice that in both examples, we get a trinomial expression when we expand the square of a binomial. To better understand the square of a binomial, let's visualize it geometrically. If we think of a and b as the sides of a square with side length a plus b, then the area of the square would be a plus b squared. We can also break down this area into 4 parts. A square with area a squared, another square with area b squared, and 2 rectangles each with area a times b. So the total area is a squared plus b squared plus 2 times a times b, which gives us our formula. A plus b squared equals a squared plus 2ab plus b squared. Let's compare our 2 examples to see the pattern more clearly. In our first example, we expanded 2x plus 3 squared to get 4x squared plus 12x plus 9. In our second example, we expanded 5x plus 2xy squared to get 25x squared plus 20x squared y plus 4x squared y squared. Notice the pattern in both cases. The first term is the square of the first term in the binomial. The middle term is twice the product of the 2 terms. The last term is the square of the second term in the binomial. This pattern always holds when squaring a binomial, which makes this formula very powerful and widely used in algebra. Let's talk about some common mistakes students make when squaring binomials. A very common error is thinking that a plus b squared equals a squared plus b squared. This is incorrect. Remember, we need the middle term, 2ab. To summarize what we've learned today, the square of a binomial a plus b squared equals a squared plus 2ab plus b squared. This formula allows us to quickly expand expressions like 2x plus 3 squared or 5x plus 2xy squared without having to multiply them out directly. Understanding the geometric interpretation helps reinforce why the formula works, and being aware of common mistakes will help you avoid errors in your calculations. Before we dive into our examples, let's first understand the key formula we'll be using. The square of a sum can be written as a plus b squared equals a squared plus 2ab plus b squared. This means that when we have an expression of the form a plus b, all squared, we can expand it by squaring the first term, adding twice the product of the 2 terms, and then adding the square of the second term. Let's start with our first example. We want to calculate 105 squared. While we could just multiply 105 by itself, we can use our formula to find the result more efficiently. First, let's rewrite 105 as 100 plus 5. So we have 100 plus 5 squared. Now, we can apply our formula. A plus b squared equals a squared plus 2ab plus b squared. In this case, a is 100 and b is 5. Now, let's apply the formula. We have 100 squared plus 2 times 100 times 5 plus 5 squared. Let's compute each term. 100 squared is 10,000. 2 times 100 times 5 is 1,000. And 5 squared is 25. Finally, we add all these terms together. 10,000 plus 1,000 plus 25 equals 11,025. So 105 squared equals 11,025. Let's move on to a more complex example with variables. We want to expand 5x cubed plus 3x squared, all squared. Again, we'll use our formula. A plus b squared equals a squared plus 2ab plus b squared. In this case, a is 5x cubed and b is 3x squared. Now, let's apply the formula. We have 5x cubed squared plus 2 times 5x cubed times 3x squared plus 3x squared squared. Let's compute each term. 5x cubed squared equals 25x to the 6th power. 2 times 5x cubed times 3x squared equals 30x to the 5th power. And 3x squared squared equals 9x to the 4th power. So our final answer is 25x to the 6th power plus 30x to the 5th power plus 9x to the 4th power. Let's try one more example with multiple variables. We want to expand 2x, y squared plus 3x squared y, all squared. Using our formula again, we identify as 2xy squared and b as 3x squared y. Applying the formula, we have 2xy squared squared plus 2 times 2xy squared times 3x squared y plus 3x squared y squared. Let's compute each term. 2xy squared squared equals 4x squared y to the 4th power. 2 times 2x, y squared times 3x squared y equals 12x cubed y cubed, and 3x squared y squared equals 9x to the fourth power y squared. So our final answer is 4x squared y to the fourth power plus 12x cubed y cubed plus 9x to the fourth power y squared. We need to expand the expression negative a minus b quantity squared. We'll apply the square of a difference formula. According to this formula, negative a minus b quantity squared equals negative a squared plus 2 times negative a times negative b plus negative b squared. Let's simplify this expression further. Negative a squared equals a squared. Since the square of a negative number is positive, 2 times negative a times negative, b equals 2 times a times b, since two negatives make a positive, and negative b squared equals b squared. Therefore, the final result is a squared plus 2 of plus b squared. Now, let's move on to our second example. We need to calculate 235 squared minus 230 squared minus 5 squared. First, let's recognize that 235 squared minus 230 squared is a difference of squares. We can write 235 as 230 plus 5. So we have 230 plus 5, quantity squared, minus 230 squared, minus 5 squared. Let's expand the first term. Using the binomial formula, 230 plus 5, quantity squared equals 230 squared plus 2 times 230 times 5 plus 5 squared. So our expression becomes 230 squared plus 2 times 230 times 5 plus 5 squared minus 230 squared minus 5 squared. We can simplify by canceling out 230 squared and 5 squared terms. 230 squared cancels with negative 230 squared, and 5 squared cancels with negative 5 squared. This leaves us with just 2 times 230 times 5, which equals 2300. We want to expand the expression a plus 1 squared. To expand this expression, we need to use the perfect square formula. The perfect square formula states that a plus b squared equals a squared plus 2ab plus b squared. Now, let's apply this formula to our example. In a plus 1 squared, we can identify that a is equal to a and b is equal to 1. Substituting these values into our formula, we get a squared plus 2 times a times 1 plus 1 squared. Let's visualize this algebraically. We can think of a plus 1 squared as the area of a square with side length a plus 1. This square can be divided into 4 regions. A square with area a squared, 2 rectangles each with area a, and a small square with area 1. So the total area is a squared plus a plus 1, which simplifies to a squared plus 2 a plus 1. This matches our algebraic expansion. Now, let's look at our second example, 1 plus b squared. Again, we'll use the perfect square formula. In 1 plus b squared, we identify that it is equal to 1, and b is equal to b. Substituting these values into our formula, we get 1 squared plus 2 times 1 times b plus b squared. Let's visualize this one as well. We have a square with side length 1 plus b. This square can be divided into a square with area 1, 2 rectangles each with area b, and a square with area b squared. So the total area is 1 plus b plus b plus b squared, which simplifies to 1 plus 2b plus b squared. This matches our algebraic expansion. Now, let's compare our two examples. For a plus 1 squared, we got a squared plus 2 a plus 1. For 1 plus b squared, we got 1 plus 2b plus b squared. You can see that both follow the same pattern from the perfect square formula. To summarize what we've learned, the perfect square formula is one of the most important algebraic identities you'll use in mathematics. Practice expanding different expressions to become comfortable with this pattern. In future lessons, we'll explore more algebraic identities. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.